last year, sir. That is in my university. So very happy to invite you today. Please.
Now, sir, I would like to thank coordinators, PhD, for having given me an opportunity to be a part of this one big family talk. So the topic Dr. Sharmila asked me to talk about powerful analysis, but I wonder, most of you have already studied this in your undergraduate as well as in your postgraduate program. I was really wondering why I have to discuss, why I have to talk this fundamental topic, but still I have accepted and I have brought the slides, presentation slides. Can you please come to the front because I am not using mic, so it may not be audible. Don't mind, please. I would like to mention the field of my specialization. One is power flow. Number 2, economic load dispatch. Number 3, optimal power flow. Number 4, placement of facts devices and DGs, state estimation, and so on. Right? So if you want to discuss, I mean, in addition to this, I in general use nature inspired optimization algorithms. Nature inspired optimization algorithms like genetic algorithm, Parkinson optimization, and other all algorithms. I have been using this for quite 20 years. Right, if at all, because I know most of you are faculty members and researchers. If at all you wish to discuss, because we can discuss at any point of time, you can learn this powerful analysis. Later we will discuss. But if at all you want to discuss anything relating to these research topics, let us interact, let us discuss. Maybe it would be say mutual benefit to both of us. Maybe I will get to know about your problems, and if possible, I will try to give you the solution. That way, I want this lecture to be more interactive rather than say traditional lecture. Even we can skip this power flow presentation because you will get it in the textbook. Maybe you can start discussing with me. Then I will try to. If anyone is doing research, yes, please you can. Yes, you can interact because maybe I am not specialized in power dynamics. Please, right? I am working only in the area of power systems. Or if you throw the problem, I will try to tell you how to solve that problem using evolution algorithms. What is the methodology to be adopted in formulating the problem? Because any problem can be formulated as an optimization problem. The problem can be anything. Right? If you want to travel to say Singapore, right? That problem can be mathematically modeled as an optimization problem and can be solved using say genetic algorithm or particle swarm optimization. Any problem can be modeled. The design of this building, design of an engine, the structure of the design of a structure, the shape of visa, anything can be formulated. So if you throw mathematical equations, then that problem can be mathematically formulated as an optimization problem. Then if you have the capability to form as an optimization problem with an objective subject to constraints, then quite naturally the formulated problem can be solved using any one of these swarm intelligence algorithms. If you don't have any doubt or something like that, yes, please.
Reactive power compensation.
Reactive power compensation.
Locally, if you are adding the capacitors to compensate the reactive
Yes.
power locally, how to size that capacitors and how we can optimize?
Yes. If you think that problem is called the optimal reactive power flow. The problem is called optimal reactive power flow. make it different from optimal power flow in the sense that in optimal power flow we attempt to minimize the real fuel cost. We attempt to minimize fuel cost wherein the real power generations are adjusted. Whereas in optimal reactive power flow, we do not consider real power generations. Instead, we consider generation voltage. The voltage of all generators, transformer tap position, and reactive power at capacitor buses or war sources in general. It can be a war source. So these three are the variables. By adjusting these variables, we have to minimize an objective function. It can be a single objective function or multiple objective function. In general, for the basic problem, the real power loss minimization is considered as the objective function. So this would be in general one of the main prime objective is loss. Loss is the prime objective in optimal reactive power flow, whereas in optimal power flow, fuel cost is the prime objective. So in this case, fuel cost is not considered. This is one objective. The other objective can be voltage deviation minimization. The net voltage deviation can be minimized. That is, we are expecting all bus voltages to be very closer to 1 per unit. We always, the consumer, expect the supply voltage to be 230 volts exactly. So in the same way, in the power systems, all the voltages are assumed to be expected to be closer to 1 per unit. That will be the second objective. Third objective, nowadays people are talking about voltage stability. Voltage stability, we want to improve the voltage stability. That can be another objective. And if at all you have some peculiar objective that can be added here for this problem other than fuel cost. If you add fuel cost, then it will become optimal power flow. Clear? Right. So these are all the variables, and in addition to that, the problem is we have to identify a set of values, these values that will minimize this objective, and at the same time that solution should satisfy the power flow equations. That is, all the loads must be supplied by the generations. So the sum of generation should equal the demand, and each bus, the basic load flow equation must be satisfied. So this is the set of load flow equations, and this is constraint. The voltage should be within the lower and upper limit, and similarly QGs must lie in between the respective lower and upper values. So this is the basic problem. This problem can be solved using traditional mathematical techniques like nonlinear programming, dynamic programming, etc., or it can be solved by means of swarm intelligence based algorithms like genetic algorithm, particular swarm optimization, etc. Clear? Got it?
Why don't we include?
Yes.
Why don't we include the limitation for the real power?
Real power. Yes. Here the problem is reactive power. Before that, I would like to discuss something about the difference between real power and reactive power. What is the difference? Real power can be, it's very difficult to generate real power. It's very, very difficult. But we can easily transmit real power from one point to another point. Reactive power, it can be easily generated. Even at this point, if you connect a capacitor bank, that will generate reactive power. But it is very difficult to transport reactive power from one place to another place. That's why it is recommended to connect reactive power sources at load points. Clear? Right. So your question is, there is a fuel cost of generator 1. I say AI PGI square plus DI PGI plus CA. See, this is the expression for fuel cost. Fuel cost is a function of generations, real power generations. Here we have this problem, we are talking about only reactive power. Reactive power is no way connected with this fuel cost. It's not a function of reactive power. The cost of power produced at any generating plant mainly depends upon the total amount of fuel burned, the total amount of steam injected into steam turbine. So that mainly depends upon the fuel, quantity of fuel consumed. Clear? So if you want to include fuel cost here, then we have to adjust PGs. Then PGs will come into here, which are PGI, I varies from 1 to 2. So if you include this as a variable, then that we will have control over the fuel cost. Then we can include that as an objective. If we include that, then that problem is considered to be optimal power flow. Clear? With this, only by adjusting these parameters, we can control only the reactive power, we can control only the magnitude, voltage magnitude, reactive power, etc. etc. So that's why in optimal reactive power flow, we do not include fuel cost here because we do not include this, we do not consider these as variables. Clear? Right.
Still, the current flow is influenced by reactive. The loss is decided by current which is flowing in the line.
Yes.
So, current attribute of both the active component and reactive.
Yes.
If you don't have a control over the real component of current, then still the loss would be decided by only the reactive component.
So for a given demand, for a given demand, say 1000 megawatt demand, right? So there may be say for example 5 generating plants. Those 5 plants have to supply meet the demand. However, anyhow it has to supply the power. It has to be generated only by those 5 generating plants. Whereas reactive power, we have capacitor plants at different locations. We can control the reactive powers at various points depending upon the nature of load. So the reactive current can be controlled. For example, if you have a transmission line, you consider this transmission line. Here we have a load of 5 plus J, say 4. This is the net demand. Here, this is the generator. Here, it has to generate 5 per unit of power. Then only the load can be met. If it has to generate that, let us timing forget about the relationship between P's and Q's. So then let us assume simply sum. So it has to carry a current of 9. So 9 I square R, 9 square into R will be the power loss. If you can connect a capacitor bank here, and if it supplies the locally the 4, then this current can be reduced to 5. We cannot eliminate 5. But we can eliminate 4. We can effectively control reactive power at different locations, and we will attempt to minimize. So reactive power will have more influence on the loss. If you compensate all the buses by reactive power, by nature the losses due to reactive power flow can be totally eliminated. But that is not practically feasible because it requires huge investments. So what is the government? For example, if I am an engineer, so I have control of say 100 nodes. So government will give only 5 capacitor banks, that's all. Okay, that is the quota given to me. So I have to place it in appropriate place, optimal place that will attempt to minimize the loss to the best possible point.
Sir, in a substation, so 110 kV voltage, but the BHEL is supplied of 132 kVAR.
132
kV
kilovolt
kVAR.
Instead
Instead of 110 kV.
kilovolt ampere reactive.
No. Instead of 110 kV bus, they are supplying 132 kV, 350 ampere.
Capacitors. No, usually capacitors break.
It attain good full effect only if it reaches 132 kV. But bus is 110 kV.
It's in general, while choosing a certain say capacitor or something like that, if you exactly choose the rating as say 110, what will happen if it slightly increases? Losses will increase and the chances of damage is more. So in general, we choose equipments little higher voltage.
But in the formula, the maximum is only at
That is the optimal case. But in general,
it's
for
cycle product, it's not a straight line. So we will achieve if the voltage is more than 110.
the objective there will be to improve the withstand capability of that unit. Because here we have spikes. During night time due to Faraday effect, what happened? The voltage shoots up. Right? To avoid that, to avoid the chances of damage, so probably that engineer would have chosen that 132 instead of 110.
Purpose could not be solved.
Anyhow, it's there.
Then what is the how to rearrange that the capacitor value? Because we are having 32 or
No, still, as an engineer, in our situation, in Indian situation, we cannot exactly maintain the voltage exactly at 110 kV. So it is better to have little higher rated capacitor bank. Right? There is no way. No, if you go for optimal thing, right? If you go for optimal 110 exactly, if due to some reason, if voltage goes up during night time, say 120, sir, yes, shoot up to 120. By the time the capacitor will be damaged. Here, so when you apply more voltage than the rated voltage, the loss component will be much higher than the normal. All of a sudden rapidly increases. Because of that, the loss component will be much higher. Right? So it should be highly erratic, non-linear.
my question, how to optimize? In normal, not sufficient 9 hours, we will step down using OLDC, we have stepped down. The voltage, first minimize the voltage.
See here, what the entire thing, what we are attempting to do is approximate them. And especially for this kind of reactive power optimization, you can't exactly get the best point. You can't because what we do all simulations based on certain approximations. For example, transmission line. Do we have exact model? What we have is only 5 model, approximate model. So we cannot everywhere we do approximations. Even in missile control, we do apply so many approximations. We can't exactly model. If you do exact modeling, then it would be taking huge time even for this side. Okay. In general, the largest generator, in general, because say let us say demand is 800 megawatts. This is the total load. These 3 plant has to supply. So for load flow analysis, we want one generator to be slack generator. So that generator is usually chosen. That is, the largest one is usually chosen as the slack generator. That's one criteria. Another criteria, the one whose fuel cost, total generation cost is much lower than the other units, because it has to meet the difference in generations. For example, because in load flow what we do is we do not specify. Maybe later I will explain the load flow, because the topic given by the coordinator is load flow analysis. Later we will discuss. So this is the slack, right? So in general what we do is this is 300, this is 200. Only at the end of load flow analysis we will be able to make up the loss, P loss. The loss is, say, if it is 10, then 300 plus 200, 500, 500 plus 10, 510. This 800 minus 510 will be 290. So it has to supply 290. In case if the loss is say 20, and the addition 10, it has to supply 300. So it is fluctuating. It should be in a position to supply larger power. So variation should be larger. So usually largest generating plant is considered as the slack generator. Anything else? Or let us pass on to our topic, load flow. Because may be boring, I think. That's why it's such. What's power flow analysis? First, let us raise the question. So before that, let me want to clarify one thing. What's the difference between linear and non-linear equations? So before going into that particular power flow analysis, let us discuss about linear and non-linear problems. So what's linear problem or what is non?
The response is not exactly following the laws.
Yes.
Whatever the output, which cannot be exactly defined by the input.
Anyone?
So if it follows the law of superposition and homogeneity, we call it as a linear system.
Second order.
So if it follows, if a system follows the principle of superposition and homogeneity, we call it as a linear system.
Anyone? As faculty members, we should be familiar with these fundamentals. Because this is very most important as a faculty member of electrical engineering. Because in electrical engineering, most of the equations, except resistive circuit, most of the equations are non-linear equations, and most of the fault running, whatever be the equipment, most of the devices are modeled by non-linear equations. Right? So if any equation is modeled by a straight line, the variation response is modeled by a straight line, that is considered to be a linear equation. If a response is does not follow a straight line, then all the equations are considered to be non-linear equations. For example, you consider y is equal to 2x. This equation is linear equation because for this equation the solution can be obtained in single stroke, in single process, single mathematical process, maybe addition, subtraction, multiplication, etc., etc. Single operation, we will be able to get the solution. That kind of equation is called linear equation. For example, 2x is equal to 10. X, anyone can say 10 divided by 2 is equal to 5. So the equation, the solution can be in single stroke, can be obtained. That kind of equation is considered to be linear equations. So other examples can be 2x1 plus 4x2 is equal to 10, 3x1 minus x2 equal to 7. I have arbitrarily written two simultaneous equations. These two equations are considered to be linear because the solution can be obtained in single stroke, single iteration. So we are all familiar with these two equations because right from the beginning we have been solving these equations. The other equations, let us consider y is equal to x squared. I want to find say value of x. X squared is equal to 10. How do you find the value of x? Square root, yes. Square root. What is the solution? If I say 9, maybe we can say, so okay, let us consider 9. 9. So as we know, that is 3 square is 9, we can tell x value is 3. But for a computer, we have to educate, we have to tell how to calculate the value of x. But similar to this equation, we cannot solve this problem, though this is the simplest problem. Because the response here is non-linear. This is considered to be non-linear equation. So the methodology to be adopted is, we have to assume a value of x naught, that we can by trial and error, we can give you a value, say 2. So first we have to assume a value. So even the calculator does this. The calculator initially starts, one assumes some value. So let it be x2. Then what we have to do is, let us consider this is function. So delta f is equal to 9 minus x squared. The difference. So we assumed that 9 minus 2 square we will be getting some value. This is considered to be error, delta error. Once this delta is, what is this? 9 minus 4 will be 5. So delta, this is error, and we have to consider the derivative of 2x. So 2x inverse into 5, that will be giving the correct values. So we have to repeatedly solve this equation. We will be getting 1 delta x. That error may be say 0.5. Then what we have to do is we have to add in this 0.5 it will become 2.5. Then once again calculate the difference. Repeat this process. So even to solve this simple problem, it requires an iterative process. So that is nonlinear equation. So what we do is, we in general, for example, sin x. If you represent this, it's not represented by sin, it's represented by this kind of curve. What we have to do is, we approximate, initially choose this value, then from this at that point, if you choose this as the starting point x0, at that point we have to linearize the problem. For the linearized problem, we will get a solution and improve the solution. We will be getting a next operating point. From that point, once again obtain the linearized solution. Repeat this process till there is no change in the final solution. So what we do is, we move. This may be the x0 initial point. This may be the final point x final. What we do is, we cannot straight away go this place. We do small change. So this is first iteration, second iteration, third, fourth, fifth. Only after 5 iterations, 5 calculations, we will be able to reach the final x. So this is the nonlinear equation. So the equations that contain square, sin, cos, e power x, log, etc. are considered to be nonlinear equations. So this nonlinear equation can be solved by mathematical techniques, the traditional mathematical techniques. Those techniques are Gauss method, Newton method. Those are the traditional mathematical techniques. Okay, traditional mathematical techniques. So in power systems, most of the problems are nonlinear problems. It involves real power and reactive power. Even if you say voltage, it is a complex quantity. The whole problem is nonlinear problem. Whatever we do, it's only nonlinear problem. Clear? You got it? So what is power flow analysis? Power flow analysis is the determination of all bus voltages. If you say bus voltage, it's not a single quantity. It has 2 components. One is voltage magnitude and its angle, voltage angle. Clear? So we have to find V's and deltas for all buses for a given set of generations and given set of loads. That problem is known as power flow problem. So first thing is voltage magnitude and their phase angles. In addition to that, reactive power generating buses. So this is reactive power generating station. For example, real power is generated, so 100 megawatt power is maybe generating. They will set some voltage, but reactive power we do not know. So reactive power depends upon the power consumed by the entire grid. So it depends upon the voltage of the generating station as well as the voltage at the load point. Right? So that also can be calculated. That can also be determined, calculated at the end of load parenthesis. Real and reactive power generation at slack bus. Only slack bus, voltage magnitude and angles are known, and transmission losses. So these parameters can be calculated, can be obtained at the end of load flow. So it involves a solution of a set of nonlinear equations. So similar to this, it has a set of nonlinear equations. A set of equations equated to some certain constant. So we have to apply some mathematical technique to obtain this solution. That is known as power flow solution. Clear? We can use some techniques. So it is mainly adopted in planning, design and operation. So without the knowledge of power flow, we cannot do research in power systems, because all the problems in power system involve load flow analysis. Before starting the say some other process, we have to first carry out load flow. So load flow is the most important study in power systems, without which you cannot do any other research. This is the most fundamental thing. So this is known as power flow analysis. So in power systems, the buses are classified into 3 categories. One is slack, another one is generator, third one is load. Slack is also generator bus, but one of the generator is considered to be slack generator, and the rest of the generators are considered as generator bus or PV buses, and the load buses are considered to be PQ buses. In each bus there are 4 variables. Each bus There are four variables. One is P, Q, V, and its angle delta. These are four are the variables. So here V and delta, P and Q. These four are the variables. Among the four, two are usually specified, and the problem, outflow problem, is to determine, calculate, obtain the values of other two parameters. So for a given two values, we have to determine the other two. That's the power flow problem. That is a power flow problem. For example, in slack generator, V and delta are specified. V, voltage magnitude of generator, delta, the angle is 0, and the P and Q are not specified. At the end of load flow, we have to calculate P and Q. And generator bus PV buses, P and V are specified. For example, naval, you consider naval. The real power generation is known. Real power generation is known. The terminal voltage is known. So P and V's are known. Q and deltas are unknown parameter for generator buses. Load buses, you consider Chennai. That load is known. P and Q's are known. But its terminal voltage, we cannot predict the voltage at this point. We have no control over this voltage. So V's and deltas are unknown parameters. These and unknown. So the problem is, for these known parameters, we have to process these known parameters, and we have to calculate these unknown parameters. That process is known as load flow problem, load flow analysis. Right. So before discussing in detail about power flow analysis, let us see the fundamental equations, basic equations. Voltage, if you say voltage, in general we call say 230 volts. It represents only the RMS quantity. But in power system analysis, we can represent these quantities by different ways. Depending upon the requirement, some may use rectangular components, some other may use polar components. Some may mix both. Say VI is equal to, VI represents voltage magnitude angles can be represented in polar form. It can be represented, can be converted to rectangular form, this to this, VI cos delta I plus J sin delta I. That real part is represented EI plus JFI. So voltage can be represented by any one of these forms. Depending upon the requirement, we will substitute the forms, any one of these forms in the equations. And there is another parameter that is called the bus admittance matrix. That is the most important matrix in power systems. For any system, we have to form bus admittance. By means of inspection, we have to form that admittance. For example, if the size of the system is 100, the bus admittance matrix size is 100 by 100. Just by inspection, we can form the matrix. The whole matrix is a complex matrix. It has conductance and susceptance. It can be represented by means of magnitude and its respective angle, and it can be conductance and susceptance, G plus JP. So it's very important, and anyone working on power systems, this is the most important. You should be, in general, people know about bus matrix. So these are the various forms. And current IA is equal to, it can be calculated simply sigma Yij Vj. This is the current. So the product of voltage and current gives the power. So morning also one gentleman asked about the doubt about VI conjugate in IA. Someone has asked. So in general, for power, if you multiply two values, for example, for V and in DC, if you multiply V and I, you will get directly power. That's real power. In case of this power system equations, the most important thing is, if you multiply V into II, you will get conjugate of power. That is, the imaginary part Q will get other side. So what we do is, we in general keep this. We have to keep this in our mind heart always. It's most important. If you want to calculate power, P plus JQI. If you want this to be plus sign, because we want this to be plus sign. We want this value to be specified just like an ordinary value. So Pi plus JQI, if you want to put it, then the equation must be Vi into Ia conjugate. Vi into Ia conjugate or Vi conjugate into Ia. Only then you will be getting both quantities to be positive. What variables can be positive. So the values coming can be directly used in the subsequent calculations. So for that reason, we have to always do this operation for calculating the power. Vi into Ia conjugate. that is VI into sigma, so called Yj into Vj. If you do this, you will be getting complex power. Right. So the substituting, so that is power is VI into IA conjugate. Here I have given different forms. VA can be polar form, rectangular form, etc., etc. Similarly, this can be in polar form and rectangular form. So in this equation, YA can be rectangular form or in polar form. VJ can be polar form or rectangular form. If you substitute all the quantities in polar form, you will be getting one form of equations. If you substitute rectangular form, you will be getting another set of equations that looks different but use the same value. If you substitute the values, you will be getting the same answer. So if you do that, so if you mix both the polar and rectangular, then we will be getting another equation. So let me concentrate on hybrid form because as teacher, this is the most convenient form to do hand calculations. For example, if you use rectangular form, what happens? Voltages are in polar form. So for each and every step, we have to convert voltage into rectangular form. If you use this equation rectangular form, you have to voltage maybe Y bus is in rectangular form in general. So voltage may be converted to rectangular form and then can be substituted. If it is in say polar form, admittance element can be converted into polar form and then can be used. But here that's why it's called hybrid form, wherein the voltage that is the available form can be directly substituted. VI, Vj and E, that is voltage is in polar form, so that can be straight away substituted, and admittance is in rectangular form, that can be straight away substituted. So do this substitution and then after some mathematical manipulations, you can take out the real part and imaginary part. We will be getting two equations. This is PI is equal to sigma VI Vj Gij cos del I minus del J plus. This equation represents real power generation at ith bus and this is the reactive power generation at J plus. Reactive power generation at the same ith bus. So these two equations can be used to calculate the real power and reactive power if these voltages and its angles are known. These and G's are system parameters. It can be formed from the system parameters. So the only variables are VA, Vj, delta and delta J. If those two parameters are known, we can substitute those parameters here and we can calculate PI and QI. Right. So I will show you the other form. The voltages are in polar, admittance is in polar. So this is the final equations. These two equations are generally available in textbook. This is the polar form. This is the equation available in textbook. And other form, this is the rectangular form. All the quantities are rectangular substituted and separated out. So in general, for software developer for a company, they use rectangular form because this is very fast. It doesn't require any sine or cosine terms. Sine and cosine terms are again an iterative process. Sine of certain angle requires an iterative process that takes finite time. Whereas if you use the same in rectangular form, the overall execution time of the overall program will be drastically reduced. So for that purpose, this is the convenient form. But in the textbook, this form is commonly adopted. But as a teacher, it is convenient to use hybrid form. Here, you got it? The difference. Right. So this is the hybrid form. So it will be very convenient. We can say straight away substitute the available values and we can calculate power. So before discussing this mathematical equations, let us see a sample system. Say